In this lecture video, we're going to learn about the central limit theorem. The central limit theorem tells us that for a population with any distribution, the distribution of the sample means approaches a normal distribution as the sample size increases. This tells us that even if a population is not a normal distribution, if we look at large enough samples, the means of those samples will be normally distributed. We use the notation mu sub x bar to notate the mean of the sample means, and it will be equal to the mean of the population. For the standard deviation, we use the notation sigma sub x bar, and it's equal to the standard deviation of the population divided by the square root of the size of the samples. What we are given is a random variable x that has any distribution that may or may not be normal. It has a mean mu and a standard deviation of sigma. And we have simple random samples, all of the same size n, selected from this population. And what we find is that the distribution of the sample means approaches a normal distribution as the sample size increases. Here are some practical rules that are commonly used alongside the central limit theorem. If we have a population with any distribution, and we have samples of size n greater than 30, the distribution of the sample means can be approximated reasonably well by a normal distribution. If the original population happens to be normally distributed, then for any sample size n, the sample means will be normally distributed. And if the sample sizes are less than or equal to 30 and the original population is not normally distributed, then the methods of this section simply do not apply. In other words, we need our sample sizes to be large enough, or we need our original population to be normally distributed. If we don't have either one of those, then we cannot use these ideas that go along with the central limit theorem. When we are working with individual x values, we calculate the z-score by using the equation that z is equal to x minus the mean divided by the standard deviation. When we are working with a collection of sample means, we need to make sure that we use the appropriate mean and the appropriate standard deviation when we calculate our z-scores. Here, z is equal to x bar, the sample mean, minus mu sub x bar, the mean of the sample means, divided by sigma sub x bar, the standard deviation of the sample means. Since the mean of the sample means is the same as the mean for the population, this is equivalent to z equals x bar minus mu, the population mean, divided by the standard deviation for the sample means. But that is also equal to sigma, the standard deviation for the population, divided by the square root of the size of each sample. The most important idea here is to make sure that you are using the correct mean and the correct standard deviation for each situation. Let's take a look at an example. Here we are given that the weights of men are normally distributed with a mean of 172 pounds and a standard deviation of 29 pounds. First, let's make a quick note that our population is normally distributed. This means that our sample sizes can be anything and we can still use the ideas of the central limit theorem. First, let's find the probability that one randomly selected man will weigh less than 165 pounds. For our population of men, we have a mean of 172 and a standard deviation of 29. We need to find the probability of a randomly selected individual data value being less than 165. Let's add these details to a normal curve. Our x values here are given as weights. We are centered on a mean of 172, and we have a standard deviation of 29. Finding the probability that a given x value will be less than 165 is equivalent to finding the area under the curve to the left of 165. Translating these to the corresponding z-scores, where the mean is 0 and the standard deviation is 1, when x is equal to 165, z is equal to 165 minus 172 divided by 29, or z is equal to negative 0.24. Let's use our z-table for this one. Looking at our table corresponding to negative z-scores, we find that a z-score of negative 0.24 has a left area of 0.4052, which means that the probability of a randomly selected man weighing less than 165 pounds is equal to 0.4052, or just over 40%. Now let's look at a slightly different probability with this same situation. We'll find the probability that 20 randomly selected men will have a mean weight that is less than 165. In Part B, these 20 randomly selected men are a sample of size 20. And we want to find the probability of a sample of this size having an average or a mean that's less than 165. This is different than finding one man that weighs less than 165. But since we have a normally distributed population, we can use the central limit theorem to calculate this probability. The mean of the sample means is equal to the mean for the population, so it's 172. The standard deviation is equal to the standard deviation for the population divided by the square root of the size of the sample. So in this case, we have 29 divided by the square root of 20, which is 6.48. This time, we are finding the probability that a given sample of size 20 will have a mean that is less than 165. Our picture in this case will look very similar. Our data values are sample means, and in this case, that's mean weight for samples of size 20. Our mean of the sample means is still 172, and our standard deviation for the sample means is 6.48. And again, we want to find the probability that a particular sample mean will be less than 165. We want the area to the left of 165. We again will translate to our z-scores, where the mean is 0 and the standard deviation is 1. And we'll find the z-score that corresponds to 165. This time, we have z equal to 165 minus 172 divided by 6.48, or negative 1.08. Notice that the z-score in Part B is not the same as in Part A. We have a different standard deviation. And looking at our z-table, we find that a z-score of negative 1.08 has a left area of 0.1401. That's significantly smaller than our area last time. 165 is more than a standard deviation away from the mean. So if we wanted to correct our picture, we could change it to something like this. We found that the probability of 20 randomly selected men having a mean weight less than 165 is equal to 0.1401, or just over 14%. It's one thing to find one man that weighs less than 165. It's an entirely different thing to find a group of 20 that have an average less than 165. Let's take a look at a different example. Here we're told that the weights of 3-year-old girls are normally distributed with a mean of 30 pounds and a standard deviation of 7 pounds. We'll find the probability that if an individual 3-year-old girl is randomly selected, her weight will be greater than 42 pounds. In this situation, we have a population mean of 30, a standard deviation of 7, and a data value that we are interested in of 42. This data value's corresponding z-score is given by 42 minus 30 divided by 7. So z in this case is 1.71. Let's draw a quick picture to go along with this. We want to find the probability of a randomly selected 3-year-old girl weighing more than 42 pounds. That's the area in this right tail. And that corresponds to a z-score of 1.71. Let's use our calculator this time to find that right area. Using the normal CDF function, we can enter our lower limit, our z-score, 1.71. Our upper limit is infinity, and we can represent that by a very large number. Our mean is 0, and our standard deviation is 1. Pasting that, we find a right area of 0.0436. Depending on your style of calculator, you may be able to use our original data values from the original scale rather than z-scores. In that case, our lower limit would be 42. Our upper limit would still be our very large number, but the mean would be 30 and the standard deviation 7. Pasting that, we find a very similar but slightly different answer. This is mostly due to the fact that we rounded when we calculated our z-score, so we do lose a tiny bit of accuracy. Using the value we found with the z-score, we have a right area 0.0436. So the probability of a randomly selected individual 3-year-old girl weighing more than 42 pounds is just over 4%, or 0.0436. Now, instead of looking at an individual girl, let's now find the probability that 40 randomly selected 3-year-old girls will have a mean weight that's greater than 42 pounds. We are now interested in the mean of the sample means, which is the same as the original mean, or 30. We also need the standard deviation of the sample means, which is equal to the population standard deviation divided by the square root of the sample size. In this case, the population standard deviation is 7, and our sample size is 40. So we have a standard deviation for the sample means of 1.107. This time our data values are sample means, or mean weights. Our mean is 30, and our standard deviation is 1.107. And finding the probability that the mean of a sample would be more than 42 is equivalent to finding the area to the right of 42 on our normal curve. This translates to a z-score equal to 42 minus the mean, 30, divided by the standard deviation, 1.107. We have a z-score of 10.84. That's almost 11 standard deviations above the mean. We should expect a very small area, or a very small probability of being to the right of 42. Once again, using our calculator, with normal CDF, we'll put in our lower limit, our z-score of 10.84, our upper limit, a very large number, our mean of 0, and our standard deviation of 1. This gives us an area that is extremely small. We have 1.139 times 10 to the negative 27. That is, we have the probability of a sample mean being greater than 42 equal to 1.139 times 10 to the negative 27. If we were to write this out, we would have 26 zeros before our 1139. So rounding to 4 decimal places, this probability rounds to 0. Once again, it is a very different probability to find one individual that weighs more than 42 pounds than to find an entire collection of 40 that have an average or a mean weight over 42 pounds. This is also a great time to remind you to make sure to use the correct standard deviation when you're working with sample means. That is what made all of the difference in these calculations. That concludes this lecture video on the central limit theorem.